So this section is called Other Worlds, an Introduction to the Solar System. So we're just going to do kind of an overview of the solar system in this chapter. The solar system is really the sun and everything that orbits it. The vocabulary for this section begins with asteroids and comets and chemical differentiation, Jovian planet, half-life, meteorite. This is mostly in alphabetical order. Planetesimal, radioactivity, solar nebula, and terrestrial planet. Not necessarily in that order. So we're just going to begin with sort of an overview, and that kind of starts with just the solar system in general. And so if you look at the table here, it shows the objects listed and their percent mass of the solar system. And so the sun is 99.8% of the total mass of the solar system. That is, everything else adds up to 0.2%, or 2/1000ths of the mass of the solar system. Now, if you look at Jupiter, Jupiter is 0.1%, so half of what isn't the sun is Jupiter. The next thing listed is comets, and comets are somewhere between 0.0005 and 0.03. So if what's left is 0.1%, then comets are up to 30% of what is left after the sun and Jupiter have been taken out. So a lot of mass in those planets. Close to the mass of Jupiter is potentially in comets. You can see how uncertain that number is, though. All the other planets and dwarf planets add up to about 0.04%. And then moons and rings, I can't even count that many zeros, 4 zeros and a 5, asteroids and cosmic dust. So you can see primarily the mass is in the sun, and of what's left, Jupiter is about half of what's left. Okay, so let's go on here. We've got basically two types of planets. Terrestrial planets are small, dense objects that are near the sun. The terrestrial planets are Mercury, Venus, Earth, and Mars. There are 4 of them. And then the Jovian planets are the larger planets that have a lower density and are farther from the sun. They're sometimes called gas giants. And those are Jupiter and Saturn and Uranus and Neptune. Sometimes Uranus and Neptune are called ice giants. By the way, there are also dwarf planets, which I mentioned earlier, and we'll talk about those later. You've probably heard that Pluto is no longer a member of the club, the Planet Club. And there are reasons for that, principally that it's much more like a comet than the things we normally call planets. And so we've created a separate category for big comets and big asteroids and called them dwarf planets. And there are increasing numbers of those because we're getting better at finding them. So those are the two types of planets, and those are the big objects in the sun, in the solar system, that aren't the sun. And now there's small objects in the solar system that aren't the sun. These objects are called asteroids and comets. And so asteroids are small, dense, rocky objects found in the inner solar system, mostly between Mars and Jupiter. There are a few million in the solar system total, and their total mass is less than the mass of our moon. Our moon is 1/100th of the mass of the Earth, so you get the idea. There's not a lot of mass in the asteroids. Nevertheless, there are a million of them, or a few million of them, or something like that. Those would be, asteroids that are larger than maybe a mile in diameter, or something like that, a kilometer in diameter. The next objects are comets. Comets are icy objects of lower density. Think of a comet as a snowball, or maybe a dirty snowball. These are found in the outer solar system, usually beyond the orbit of Neptune. The solar system is messy, and so some comets stray into the inner solar system, and some asteroids get into the outer solar system. But by and large, comets are outer solar system objects, and asteroids are inner solar system objects. There are potentially trillions of comets in the solar system. Remember, I said a few million asteroids. So, and they might have a total mass near that of Saturn, whereas the total mass of asteroids is around the mass of the moon. So, very different. Describe the layout of planets. So this next graph, if you look here, this next table, I guess, is sort of properties of the planets. And so in the first column is just the name of the planet: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Those are uh, the planets in order from the closest to the sun, which is Mercury, to the farthest from the sun, which is Neptune. And sometimes people remember that as my very elegant mother just sent us nachos. I think that's what that one is. The next column is the distance from the sun. And so you should know the order, and you should know the approximate distance. So this is so if the Earth is one astronomical unit, remember astronomical unit is by definition the average distance from the Earth to the sun. That's what we call an astronomical unit. It's about 93 million miles. We call it about 100 million miles. We round it up so it's a nice even number. On that scale, Mercury is 0.39 astronomical units, or you might call it 0.4. It's a good number to round to, or 40 million miles. Venus is 70 million miles. Mercury is 1.5 astronomical units, or 150 million miles. Jupiter is about 5 astronomical units, and so it's 500 million miles. Saturn is about 10. If you look at that number, 9.54 is about 10. Or Saturn's about 1 billion miles from the sun. Uranus is about 2 billion, or 20 astronomical units. Neptune is 3. So you can create a scale model of this, and we'll do that in a minute. So let's talk about the orbital period. These are in Earth years, so Earth's orbital period is obviously 1 year. Mercury is about a quarter of a year. Venus is a little more than half. Mars is almost 2 years. Jupiter takes 12 years to go around the sun. Saturn 30, Uranus 84, and Neptune 164. Their sizes. So if you look at the size of the Earth is about 13,000 kilometers or something. That's about 8,000 miles. So Mercury is less than half. Venus and Earth are about the same size. Mars is about half the diameter. Notice that Jupiter is about 11 Earth diameters, 11 or 12 Earth diameters. So that's a lot of Earth diameters, 12 times the size. Jupiter is about 10. Uranus and Neptune are about 4. So that gives you the rough size scale for these things. You can look at the masses. This is in, 10 to the 23rd kilograms. It's a bad unit of mass, but you can just compare them a little bit, right? If Earth is 60, Venus is a little bit less than that. Notice Mercury is about a 20th the mass of the Earth, or something like that. Mars is about a 10th, right? But Jupiter is roughly 300 Earth masses, right? Saturn is about 100, and Uranus and Neptune are about 15 or something like that. 15 or 16. So it gives you a little bit of the relative size of these things. Another useful thing to look at is density. Density is the mass per volume. So iron is dense, styrofoam is not dense, right? And so if you look at the 4 terrestrial planets, Mercury, Venus, Earth, and Mars, they're all have fairly high density. The density of water on this scale is 1. And so these all have the density somewhere between rock and iron. Rock is about 3, so Mars is pretty close to rock. Iron is about 8. These guys were about halfway between Mercury, Venus, and Earth. They're all about halfway between rock and iron in terms of their average density. But look down here at Jupiter, Saturn, Uranus, and Neptune. They're all closer to 1. They're all closer to the density of water. And so the Jovian planets, the most large outer planets, are definitely chemically different than the inner planets. By the way, you can also sort of notice, if you look back over here in column 1, where we're looking at the distances, the distances from the sun of Mercury, Venus, Earth, and Mars is really small. It's up to 1.5 astronomical units. It's all 4 of them. And then Jupiter is 5, so it's more than 3 times farther away than Mars. It goes from 5 to 10 to 20 to 30. So the Jovian planets are much farther out. They're lower density. They're much bigger. They have much longer rotational periods, stuff like that. And so those are ways to think of the planets as the terrestrial versus the Jovian planets. You can sort of see it in that chart a little bit. Whoops. Oh, I lost it. So this little chart here says, you know, if you change astronomical units into meters or yards, if you want, if the sun is at the goal line, then Earth is at 1 meter or the 1 yard line. That would put Mercury at 0.4 meters, so less than half a yard from the goal line. Venus is 0.7, so also less than a yard. Mars is at 1.5 yard line. Jupiter is at the 5, Saturn is at the 10, Uranus is at the 20, Neptune is at the 30. So it kind of gives you a scale. All the terrestrial planets are within 1.5 yards of the goal line, and the Jovian planets are spread way out. So let's talk a little bit about the composition and structure of the planets. So the composition and structure of the planets, this says describe the characteristics of the giant planets, the terrestrial planets, and asteroids and comets. So the giant planets have icy or rocky cores, and then hydrogen and hydrogen compounds in the mantle, and then a gaseous atmosphere. The Jupiter and Saturn have composition similar to the Sun, about 75% hydrogen, 25% helium, and so they're very similar to the Sun in terms of their composition. They also have lots of hydrogen compounds. They just don't significantly affect those percentages. So over here you see typical hydrogen compounds are water, methane, and water, ammonia. NH3 is ammonia, and CH4 is methane. Drawn a little better down here on this, a few lines down. Hydrogen compounds are just compounds with hydrogen in them. Remember, a compound is any kind of molecule. H2O, O2, N2. These are just those are all compounds. It's molecules that have been formed by atoms, right? And the ones with lots of hydrogens in them are typically the ones we find in the Jovian planets, because there was just a lot of hydrogen in the solar system when they formed. And so there's ammonia, methane, and water, and things like that. And they also have some rocks in their cores. All of the Jovian planets do. Saturn and Jupiter are a little different than Uranus and Neptune, because they accumulated a lot more hydrogen as they formed than Uranus and Neptune did. But nevertheless, Uranus and Neptune also have lots of hydrogen and helium and hydrogen compounds. All of those Jovian planets have sort of rocky, icy cores. That's sort of how they formed. We'll talk about that more as we go. The terrestrial planets have rocky surfaces and metal cores with metal compounds in between in what we call the mantle. Planets, as you can see, we've been talking about the cores of these planets and things like that. Planets typically have their most dense materials at the core and their least dense at the surface. Whether you're a Jovian planet where you're having rocky and icy materials in your core and hydrogen and helium at your surface, or if you're a terrestrial planet and you're having iron and other metals in your core and less dense rocks at your surface. The process where the dense materials go to the middle and the lighter materials stay at the surface is called chemical differentiation, and it occurs because all of the planets formed molten hot, and so they were essentially liquid when they formed, so the densest materials sank to the bottom or sank to the center. And so all of the planets are like that, and the process is called chemical differentiation. The gas giants really might be better called liquid giants, since the pressurized interiors of them make them no longer gas, but essentially liquids on the inside. But they're certainly gaseous at their surfaces, and they look like giant gas balls. So that's why they get called that. Um, Jupiter and Saturn, Jupiter in particular, has a large amount of hydrogen in it in liquid form, and that plays a role in the enormous magnetic field it has. Hydrogen, when compressed into a liquid, acts like a metal, and so it conducts very well, and so it gets a magnetic field similar to the way the Earth does, except it's much larger. Let's just talk briefly about what influences the surface of a planet. The surface of a planet is influenced by the sun shining on it. That affects the inner planets more than the outer planets. But there's also heat coming from its interior. All of these planets formed hot, and so they've stored their heat. The Earth has still got a very hot interior. Other planets have cooled off. The littler ones, like Mercury and Mars, have cooled off mostly in their interior. But the Jovian planets are still very warm because they're so large, and it takes larger planets longer to cool off. Another side effect is planets with atmospheres tend to cool off slower because of the greenhouse effect. They hold their heat better. Venus has a very, very hot surface. It's like 860 degrees Fahrenheit, certainly hot enough to burn wood, because its atmosphere is so efficient at holding on to heat because it's so thick. Planets with geologic activity are typically the larger planets that have a hot interior. The planets without them, so if you want to think of the Moon as a planet, even though it's not really, but it's like one, the Moon and Mars and Mercury are all small enough that they've cooled off, and so they don't have much interior heat, and so they don't have any geologic activity. Geologic activity, so if you see volcanoes active on a planet or geysers or something like that, that indicates there's some heat going on inside. Some interesting things happen, like the Jupiter's moon Io is heated by tidal forces from Jupiter. So even though it's very small and should have cooled off by now, Jupiter is kind of squeezing it to make it get hotter. And so Io has lots of geologic activity.